Hi and welcome everybody. I'm Dr. Sam Roscoe. Today we're going to be talking about the concept of capacity, throughput, and bottlenecks. I've touched on some of these concepts already, particularly capacity and throughput in some of my other lectures, but really now what we're going to be drilling down into is the concept of bottlenecks. So what we can see here is the operations process, which we've begun to understand as a transformational process. Operations management itself is transforming inputs into outputs, and it is what happens in that transformation that gives us the operations and the operations management concept. So when we look at transformed resources, these are all of our raw materials or subcomponents or subassemblies, all of the information, our demand information, as well as if we're in a service-based operation, it could be our customers. And then we have our transforming resources, which are our facilities and our staff. Then you have these inputs coming into the process. So those will be our various transform resources and our transforming resources. The operations management process itself is the transformational process. And then coming out the other side, we should have our outputs going to a final customer. And this basically shows you that in the middle, we have a work in progress inventory, as well as we have our flow time going through our operation. Okay, so with that in mind, we have this concept of capacity. So what is the capacity of our process, or what is the capacity of our operation? Now, when we try to understand capacity, what we're thinking about is operations should be a fluid process passing through a series of steps, or in this example, a series of pipes. So the idea here is when we think about capacity, it is the upper bound on the throughput, basically meaning that in this pipe example, you have the surface area of the actual pipe, that round circumference. That is what the capacity is. So that is the maximum amount of fluid that can move through that particular pipe at any one time. And that is bound by the capacity of the pipe. And you can see that illustrated there. So the issue that we have with capacity, though, is most operations, most operations or operational processes don't run at full capacity. So capacity is a measure of the potential of a transformational process or an operation turning inputs into outputs. Now, capacity can be defined as the maximum sustainable throughput of a system. So how sustainable can this throughput go through the system at any one time, the maximum amount? In other words, capacity is the fastest sustainable rate at which inputs can be transformed into outputs. The simplest operation to analyze is one with a single resource here. So we can call this capacity of such a system is the capacity of that resource. So for example, if we have an individual who is going through a restaurant, we are going to have a set number of tables, we're going to have a set number of servers, we're going to have a set number of materials coming into the restaurant, and we will only be able to sit a fixed number of people at any one time due to the capacity or the space of the restaurant and how it's laid out. So in other words, the capacity of a resource is the fastest sustainable rate that a resource can transform inputs into outputs. So the word sustainable here is an interesting one. First, if we think about a car, the speedometer in a car may go up to 240 kilometers, such as in this example, but is that rate really sustainable? So when we look at this concept of capacity, if you drive a car at 110 kilometers an hour or 240 kilometers in the last example, the car will eventually overheat, but the driver will likely crash it before that happens, okay? The car plus the driver are your resources within this particular operation, and they probably together, they cannot exceed a rate of about 110 kilometers sustainably. Similarly, with machines, in the manufacturing process, there are high settings that will burn out a machine and are probably unsustainable. People can also be pushed to work at a very fast pace, but eventually will burn out. So the capacity here of a process flow is determined by the individual capacities of each resource, but in a somewhat non-straightforward way, meaning that the arrangement and how your resources are arranged and the number of resources that are in your operation become critical. So Just use an example here. Let's use the Peace Arch border crossing between the United States and Canada on the West Coast. Here you can see that the US border crossing processes trucks and passengers in this example. The lane of the border crossing can process a vehicle, either a truck or a passenger, in 10 minutes. A truck has an average of 1.05 people per truck on average for this particular example. A passenger vehicle can have an average of 1.9 people per vehicle, so slightly higher than a truck on average. The border crossing experiences the following demand pattern. So 30% of its traffic is trucks and 70% is passenger vehicles. So the question that I'm asking here is, what is the effective capacity of the border crossing for processing people, so not cars, but people, if there are 2 lanes open throughout the day at the border crossing? And we want to understand the people per hour, and that becomes, remember, our throughput rate. And we're trying to understand what is our throughput rate through the border crossing. So each lane of the border crossing is a resource. The 2 lanes together represent a resource pool. Okay, so 2 resources together. When calculating the capacity of the border crossing, we have to add up the capacities of each lane. So since the lanes are identical, it makes this a bit easier. We can compute the capacity of a single lane and multiply it by 2. That is, the capacity of the border crossing equals 2 times the capacity of a lane. However, the lanes process vehicles, not people, so that becomes important. That is, the natural flow unit, which of the lane is vehicles, whereas we're trying to get to people per hour. However, the question asks for capacity in terms of people per hour, so we have to make a conversion. So if we begin to look at how do we begin to solve this problem, there are 2 classes of vehicles. We know that there's trucks and passengers. We know that the average occupancy rate of each vehicle is 1.05 for a truck or 1.9 for a car. And we can begin to do some calculations. So when we look at sort of the lane capacity, we know that we can have 1 vehicle every 10 minutes. So if we look at, we have 30% of our volume is trucks at 1.05 people on average. And then we know that 70% of our volume on particular lane is cars. So that's 1.9 vehicles on a people per vehicle. Times we have 60 minutes in an hour. That equals 9.87 people that we're processing per hour on if we do 1 vehicle every 10 minutes, okay? That is the effective capacity since the proportion of trucks and passenger vehicles is imposed. However, if our goal was to process as many people as possible, then we would want to have only passenger vehicles arrive to the border because they have more passengers than the trucks. That would be the theoretical capacity in people per hour. So if we were looking at the maximum capacity of people per hour, we would really just want to calculate cars moving through that particular process or through those 2 lanes. Okay, so hopefully that shows you that the capacity depends on, first of all, your flow unit, how you're measuring the unit. That's not vehicles or people. And then trying to understand if we're looking at specifically at people, then we're better off looking at only having passenger vehicles and maximizing that capacity. Okay, so moving on to this concept of bottlenecks and understanding how do we identify those bottlenecks. A couple of tools that we can use that we're going to talk about here. There is the theory of constraints, which is always useful, and that will come into play here. And that's been made famous by Goldratt. But we'll also talk about using non-value adding and value adding time. So here we're going to use an example of an emergency room operation at a hospital. So if we look at very straightforward process, a patient arrives and books in. You then have triage where the nurse identifies the condition of the patient, what is their problem, takes their vital signs, and then you move into this diagnostics by a doctor or consultant, and recommendations are made for treatment. Okay, so if we just say that the flow time for the patient to come in is 5 minutes of the patient booking in, the triage is 10 minutes, and the diagnostics is 20 minutes. Now, what this says in this particular example, if I only had 1 patient come in, they could check in, the nurse was just waiting there, they could move directly to the nurse, and then once they're done with the nurse, they move directly to the doctor. You would be able to get 1 patient through that process in about 35 minutes, okay? However, you begin to build up additional time as you begin to move more and more patients through that process. So you can see here the total throughput time for the first patient is 35 minutes. But what begins to build is if we have a second patient who arrives, so if that patient arrives here, they then have to wait, first of all, for the first patient to go through. That's the 30 minutes. And then they might also have to wait the additional 20 minutes as the patients are building up, waiting for the doctor. Now, if I have more patients coming in after my second patient, let's say patient 3, patient 4, patient 5, we might get additional buildups of the flow time. We could have waiting time here, another 50 minutes. We then have to calculate the flow time of all the people in front of us, as well as the non-value adding time here, and the flow time going throughout the process on the other side. Okay, so who or what is when we look at this particular process, so I just go back a step, where do we see that the bottleneck is? I mean, if it's only one patient, in that particular instance, it would be the doctor, because the doctor is taking 20 minutes to isolate and identify the issues with the patient. So we can see here the bottleneck is the doctor, as she limits the flow and sets the upper bound of the capacity on the process, meaning that the time that is taken with the doctor will set the pace of the rest of the operation, meaning that the patient will have to move at a steady pace in order to make sure that we're processing everybody through that additional bottleneck. So a bottleneck can thus be understood as a resource pool that limits the flow to a system's overall capacity. So when we look at this idea of bottlenecks in the hospital example, the system can handle the system handle one customer every 15 minutes? Well, we said no, because not currently, as the capacity of the process is one patient every 35 minutes. In the hospital example, can the system handle one customer every 35 minutes? Yes, but only if the patients arrive evenly spaced out in 35-minute increments. If not, then what we have to do is each patient is going to be waiting for the next patient in front of them, and then you get this accumulated time in the process. The only way that you're able to do that is by evenly spacing out patients using appointment systems, demand management systems, or by having more nurses and doctors in order to deal with the patients that are coming through the system. So you're increasing your capacity in order to deal with the demand that is coming onto the process. So capacity then is the long-run sustainable throughput of the process. And the capacity of the process for one patient is set by the combination of the process steps. So again, we said 35 minutes. And the capacity of the process for multiple patients, assuming they arrive at the same time, that needs to include all of the steps in the process and any non-value adding time or the waiting time that begins to build up in that process. Okay, so that is sort of key things that we have to consider. That becomes sort of our throughput time. Our throughput time includes the capacity of the operation, and it also begins to build in that waiting time in the process as more and more patients go through the process. So just another example here using the process mapping that I discussed in the last lecture. What we could see here is that we have a customer who is trying to get approved for a loan. You have the customer comes in. In this example, you'll have the bank will check the loan documents and put them in order. That might take 10 minutes. Categorize the loans depending on what type of loan you're taking. That's another 20 minutes. You check the applicant's credit rating. You see if but then might enter the loan application data into your system. You then ask the question, is the loan approved? Yes or no. If no, you go back to the customer and tell them no. If yes, you complete the paperwork. So those are all the individual process steps. But the issue is that there might be time and buildup of time in between those individual stages. So here, what you can see is that you have 15-minute delay between categorizing the loans and checking the credit rating. Here, you're checking the loans and documents and putting them in order and categorizing the loans for another 20 minutes. And then you might have another 60 minutes in between entering the loan data and completing the loan paperwork, okay? So what becomes as important is the transition time between the activities is as important as the activity itself. So each of these steps for the customer adds value because they're working on the loan, they're making a decision. But if there's any delays in the process, or if there is accumulated time where that's causing bottlenecks or buildups, then we get these delays. So the issue that we have here is that you have a bottleneck in between, where the customer might be completing the paperwork for the new loan, and that is creating sort of backlogs throughout the entire system. Now, in this particular example, the bottleneck will be around the categorization of the loans. Because that's at step 2, you're already going to be building in delays throughout that process. So a really nice tool for understanding this idea of managing processes and identifying value adding and non-value adding time is a tool called value stream mapping. This is a lean tool that's been applied in a variety of different industries and applications, but it's a very powerful way of identifying value adding and non-value adding time. So the key here is about eliminating waste. And when we do talk about lean, which I will get into in future lectures, is this idea of waste could take the form of waiting time. It could take the form of excess inventory. Waste might be excess movements in a process. Waste could also be waiting time. It could be workers not working at a capacity because they don't have enough stuff to work on. So this is inefficiencies in the system. So value stream mapping is trying to identify all those non-value adding times. Focuses on optimizing the efficiency of the process, using time as your unit of analysis. So it takes process mapping and it adds in the nice addition of time to understand the importance of time in a process. By understanding what steps in a process add value to your customer or process owner or beneficiary, I'll explain that in a second, you can focus on reducing the non-value adding time. So value adding time is the perceived value of time in the eyes of the customer. So that means that as long as your customer can perceive that your product is being worked on, or in the hospital example, they're seeing a doctor, they're seeing a nurse, they're being triaged, they're being treated, that adds value. If they're just sitting around and waiting for something to happen, that doesn't add value. It just it is sort of waiting time or wasted time from the customer's perspective, non-value adding time. So non-value adding time can be understood as any steps in the process do not add value to the customer according to the customer's perception. And non-value adding time includes all of these wastes that I discussed earlier. The other thing that I should say is it's not always about the end customer. You could have in a business where your operations are making a product and the customer is the marketing department, or the marketing department is working on a new product launch and their customer is the sales department. So you can have different process owners or beneficiaries, or it might be like the CEO who is the beneficiary of an operational improvement. The customer might not always be the end customer. They could be another department in your business. So I'll just show you an example here of a value stream mapping. Within this example, let's say we're making widgets. You can see here we have our production control center within our operation. They do what's called materials requirement planning, or MRP. And in this is what's called a current state value stream map. In this example, they send out a weekly schedule to all the different machines and tell the different machines what to make. They also send out a 6-week forecast to their supplier, Michigan Steel Co. on the top. And they might also fax over an order every week to Michigan Steel Co. And Michigan Steel Co. will then deliver these 500-foot coils of, let's say, aluminum coils. They'll deliver those every Tuesday and Thursday to the back of the production line. And those coils might sit there in inventory on the sort of inbound area of the shop floor for 5 days in this example. And then they get moved off of the inventory, off of the floor. They get stamped. Okay, so when they get actually stamped, because you're physically transforming the product, that becomes value adding time for the customer. The waiting time, that 5 days where the inventory is just sitting there, doesn't add value to anybody. That becomes non-value adding time. So the idea here is that my value adding time is 1 second. And then in between my stamping and my welding operation, my inventory builds up again in that 7.5 days. I have 38 seconds to do my weld, and I have another 1.8 days worth of inventory piling up. My welding station Again, welding station 2 takes 45 seconds, another 2.5 days of inventory. Assembly takes 61 seconds, and then I have another 2 days of inventory, 39 seconds to do sort of a final assembly of my widget, and then 4.5 days for the finished product to sit on the floor before it's shipped out to our customer here, State Street Assembly, who receives in all of our products. Now, the interesting thing about this is that there are a number of bottlenecks. So as you can see, we have delays here. So the staging process is only going out, it's having daily deliveries out to State Street Assembly. And these are sort of daily orders coming from our customer into us. But we have delays in terms of our forecast, which we're only giving to our customer every 6 weeks. And then you can see here that the supplier is only, to our supplier, and then our supplier is only delivering on a Tuesday and Thursday every week. Now, if we look at this whole process flow for making widgets, you can see that our overall production lead time is 23.5 days, and our value adding time is 184 days. So because we have all of these different steps in our process, and because we are not optimizing our process, we're basically pushing as much inventory as we can onto the process. That inventory is then sort of sitting there waiting for a machine to be available. We have more and more buildup of inventory, work in progress inventory between our production steps. And we then have this issue where, within our shipping and staging system, we have 4.5 days worth of inventory buildup, and then we have all the other buildup in between our machines as a result. Now, we have to think about, when we're looking at this process, where or what can we change to give more value to the customer to sort of reduce that non-value adding time and improve the value adding time in the process. So this particular example shows the future state process map, and the idea here is we change a bunch of things. So we have our production control. Instead of sending out orders every week, we begin to send out a daily order to our supplier. Our supplier then is not delivering every Tuesday and Thursday, so not every 2.5 days, so now delivering every day. And what our supplier then does is they deliver it into the back of our facility using a process called Kanbans. Okay, so Kanbans are another lean tool, and this is the idea of using visual signals to control the pace of your operation. And I'll sort of talk you through that, because what we're doing here, instead of pushing inventory through our system, what this particular value-adding tool says is that we actually want to pull orders through our system. And the idea there is that our customer sets the pace of the operation. So if we have daily milk runs into our customer, we should be shipping out every day. And as we ship out every day, you can see here we've added in where it says L and R, left and right. We set 2 different Kanbans, and those Kanbans have basically, once those are empty, so once we pull something out of here and put it into the shipping area, that creates a blank space, and that tells our welding and assembly people to weld and assemble our widget and deliver it to the staging area. Similarly, when the right becomes empty, because we're shipping it out, that sends a signal for the welding and assembly people to make something and put it into that particular area. So what we've done here is we've used this idea of Kanbans or signals to begin to pull products through our operation. The other thing that they've done in this example is they've begun to combine different operations or different steps in the operation. So welding and assembly have been combined from the multiple welding and assembly stages that we had before into one sort of multi-skilled workforce who is able to do multiple things. And by doing that, it takes 165 seconds, sure, but you don't have the inventory building up between each of those stages waiting for our workers. So in this example, our shipping or our customer orders are really setting the pace of the operation, pulling through from our welding and assembly. And we are beginning to also pull through from our stamping, where we have that combined as well. And we're then using Kanbans again for the delivery of our products, where we're only pulling in those into our stamping operation. And once those become empty, that sends a signal to our supplier to deliver into the back of our operation using those visual Kanban signals. So when we begin to change our operation around like this, what you can see is that our production lead time has shrunk from 21.5 days, or 24 days. That's been shrunk down to 4.5 days. It's a significant improvement. And you can also see then is that our value adding time has not gone up, but the non-value adding time has come down significantly, which means that our value adding time has gone up as a percentage of our overall process. And it means that we are able to deliver to our customers quicker because our production lead time has been condensed. Okay, I'll explain more about lean principles and the idea of pull, just-in-time deliveries, Kanbans, when I do a lecture on lean. But the value adding, the value stream mapping is a really nice visual tool to begin to explain how customers perceive operations, what brings value to them, and to prioritize that when you're designing your processes to make sure that you're adding value to the customer, and they perceive that as adding value to the customer, and we are able to deliver a more streamlined service. Okay, so hopefully that is useful for everybody. Thank you for your time today, and I will leave you there. I'll see you next time. Thank you.